Let's quickly take a few minutes to talk about some corollaries of the tangent existence theorem and the converse of that. Some quick reminders. We had the tangent existence theorem, which assures us of the existence of tangents in the way that we discussed before. That is, it tells us how it is that they may be constructed. So if we have a radius in the diagram, radius AB, and we construct a line perpendicular to that radius through its endpoint on the circle, then as we prove, that line must be perpendicular to the radius. So we know that we may construct perpendiculars. So it then follows that tangents do exist, and this is how we make them, at least one way. And we also prove the converse of the tangent existence theorem, which says this, is that if we are given a tangent, so in this case we don't wish to prove that one exists, instead we are simply given that one does exist, and if we draw a radius out to the point of tangency, and we know that a tangent by definition intersects a circle precisely once, then that radius will be perpendicular to the tangent. So the conclusions are these. The original, the first theorem, if we make the perpendicular to the radius, we get a tangent. And second, if we have the tangent and then construct the radius out to the point of tangency, it's perpendicular to the tangent. Now, there's some nice consequences of this that I thought deserve their own section. The first of these is the twin tangent theorem, which says that if we have a point outside a circle, and from that point we have two tangents to the circle, in this case dB and dC, then those two tangents, that the segments from the exterior point to the point of tangency, segment dB and dC, they must be equal. And this is a simple matter to prove. If one draws in AB and AC, of course, each is a radius, so those are equal to one another. And then let us draw in AD. This will, of course, be a triangle congruence proof. AD is a common side to the triangles ABD and ACD. And notice this as well. We took a radius out to a point of tangency, which means that we make a right angle. So I'm sure that you can construct this proof on your own, but notice that it will be hypotenuse-like. That's the congruence principle that we need here. And then here's a nice corollary of a corollary. Let's say that we have two circles, as pictured, and we have a segment that's tangent to both, AC, and we have a second segment that's tangent to both, that is dB, then those must be equal to one another. And the easy way to prove this is just to imagine those two tangents extended until we find ourselves with a point of intersection, and then call that Z perhaps, and then you just simply apply the twin tangent theorem twice. Once for the circle that contains C and D, that will give you ZC equals ZD. A second time for the circle that contains A and B, that will give you ZA equals ZB. And then equals taken from equals give equals. So ZC minus ZA is equal to ZD minus ZB, from which it follows that AC is equal to BD. And we're done. Now, here's the final result that I wish to discuss, and it's a really very nice one. And there's a kind of a nice symmetry here. Remember, we had the case of the inscribed quadrilateral, and what we proved about the inscribed quadrilateral is that its opposite angles must be supplementary. This was a consequence of the inscribed angle theorem. But now let us say that we have a quadrilateral that's circumscribed about a circle. Now what does that mean? When a polygon is circumscribed about a circle, that means that each of the sides is tangent to the circle, that is intersected at one and only one point, or perhaps more precisely, each of its sides is a piece of a line that is tangent to the circle. So here's a picture to illustrate this. So we have the quadrilateral BCDE. It is circumscribed about circle A, which means that each of the sides is tangent to that circle. So here's the result. It says that if we have a quadrilateral circumscribed about a circle, then sums of opposite sides are equal. That is, form the sum of one pair of opposite sides, then form the sum of the second pair of opposite sides. Those sums must be equal. That is, in this case, BC plus DE, the sum of left and right, is equal to BE plus CD, the sum of top and bottom. Now, as for how it is that that would be proven, well, we've said that the sides are tangent, so that means we have points of tangent C, just follows by definition. Call them whatever you like, W and X and Y and Z. And then consider how the twin tangent theorem may be applied. BZ and BW are two tangents from the same circle, from the same exterior point to the same circle, as are EZ and EY, as are DY and DX, as finally are CW and CX. Now consider then what we find in the sum of BC plus DE. We find a segment with a single hash, BW, a segment with a double hash, EY, a segment with 3 hashes, DY, and a segment with 4 hashes, that is CW. Now consider what we find in the sum of BE plus DC, the sum of top and bottom. There's the single hash, there's the double hash, there's the triple hash, there's the quadruple hash. So no matter whether we sum top and bottom or left and right, we get a single, a double, a triple, and a quadruple hash. And the sums of equals, as we know, are themselves equal. So it will follow that the sums of opposite sides are equal, which is really a very nice result. Now, a question that might occur to you, and this does come up on the myriad, is this. Whether the converses of these two results about quadrilaterals are equal. The first result from the previous section was that if a quadrilateral is inscribed into a circle, sums of opposite sides are supplementary. Well, the converse conjecture at this point would be if you have a quadrilateral in which sums of opposite angles are they're supplementary, then a circle exists that passes through all 4 of its vertices. And then the converse of this one would be this. Let us say, of this new result, the result of this section would say, let us say that we have a quadrilateral in which sums of opposite sides are equal. Then there exists a circle that can be constructed inside of it such that that quadrilateral will be tangent to the circle. Each of its sides will be tangent to it. Now, as for how one proves these, that's something that's not quite um, that we're not quite yet able to do. That will require results that we will get in the concurrency chapter, which comes later in the book. But these are excellent questions, and they will be addressed later on.